Hi, good afternoon, guys, or good morning. Welcome to this coffee break, one of our series, with myself, Liam Hanna. I am the former robotics specialist, now robotics salesperson for Europe, the Middle East, for Eddyfi Robotics. And today we're going to be speaking about sort of the integration of some of our other sensor technology into robotic solutions. So the title we've given this is really better information equals better decision making, and that's really the theme of this short coffee break that we talk about now. Throughout this presentation, if people have questions, please feel free to ask these in the chat box, and these will be fed through to me live as we go through, and I'll try and answer these at the end. I'll talk a little bit about why we innovate, what are the things that drive innovation, and how we add value by using the information that we have in a robotic environment. Generally, there's a number of sensors considering the environment, and we don't always use all of that information. So how do we use that information to get the position to make the best possible decisions? I'll talk about two specific case studies. So one surface-based crawler for a magnetic solution with visual inspection, ultrasonic, pulsed eddy current, and eddy current array, and a pipeline inspection, an in-service pipeline inspection solution that doesn't require excavation, where we can do remote visual inspection, phased array UT, and laser profilometry inside a pipe at relatively long distances. We'll talk about that when we get there. I'll follow up with what our deliverable is, and that was really, I mean, essentially for me, our deliverable is providing you as a client or an asset owner with the tools and the information, I think information being the operative word, that you need to make a decision on the health of your assets. And then we can talk about the key benefits for that specific industry. So as we go into this, one of the comments that I made in a presentation around 18 months ago is that we constantly look at robots as inspection tools, which is fine. But actually, we should look at robots much more as platforms to mount tooling and maintenance equipment and inspection equipment for multiple tasks. Essentially, a robot is designed to take a human out of a dangerous environment or an environment where we don't want a human to operate for various different reasons. So there's no reason we can't look at adding multiple sensor technology to these type of things to carry out that type of inspection. I think the question that we generally pose is, why do we innovate? But I think what's probably more important is to consider really what drives innovation. Essentially, innovation is driven by our customers and the users of our equipment. And we get feedback based on what the requirements are for a specific inspection. And we look at what we can do to try and achieve that. And how do we make that safer? How do we make it so that it essentially costs less money? How do we make it with a higher quality? And then we break this down into really four key areas. The drivers for our customers most frequently are, we don't really look at developing anything unless we can look at something that will aid in improving safety. So that could be, can we provide something that allows a human to not have to work at height or inside a confined space? We look at things that will improve environmental performance. So again, by using a robot to carry out a task or a crawler to carry out a task, sometimes removes a large amount of the environmental impact, whether that is the requirement to excavate, for example, in a specific location, or even as simple as having an operator travel from one country to another country on an airplane. We look at ways to increase operational efficiency, so the ability to carry out tasks either remotely or with the ability to gather more information in a shorter period of time, which essentially aids in the final two areas, which are, how do we try and avoid the effects of cost and reduce costs as much as possible? And again, if you can do that with a robot, because of the fact that it's designed to do multiple things at one specific time, then that's a huge benefit to industry. And these are the fundamentals of why we look towards innovation and what drives innovation. The key differentiator is the fact that actually we need to gather information, and by having more information, we add more value. And actually, one of the real things that we need to try and look at more and more, and which is what we're doing now, and we talk about during this presentation, is the fact that we can start to actually use more of the information that we have available. Eddyfi Technologies, I'm sure some of you guys are aware, is we're not just a robotics company. We have multiple sensor technologies. And the ability to try and start integrating them and using those in conjunction with our robotic solutions just means that we extend our reach considerably further than we would be able to do by just using a human with their hand, either that be rope access or standard inspection techniques. Being able to operate into much more confined spaces, operating at considerable heights through pipelines of considerable distance, maybe 1 kilometer, even further, really adds value by providing information to areas that we wouldn't generally have the opportunity to gather that information from. Common applications across the majority of industries that we address include things like pipes, welds, risers, heat exchangers, obviously things like steam generators, reactor vessels, and then we look at more specific things like nuclear fuel pools, storage tanks, and then containment vessels. And you can see some images here of the various different robots being operated in this type of environment. Again, there's much more of this available in video format on our website. Sometimes we need more than just visual inspection. If you're trying to understand the health of an asset and you want to make the best possible decisions, then of course you need as much information as possible. So sometimes we can try and look at using this visual inspection system mounted to a robot, and then we start to mount other types of sensors or other types of tools, which gives us either more information or carries out a task that will try and save money, become more safe, reduce environmental impact. This can include things like remote cleaning, so surface preparation for various different operations, remote asset maintenance, so things like coatings and paint application, removal of grout and vacuum, and then of course remote handling. This is really the area where we can start to look at taking a human task and then using a robot to carry out these tasks for things such as foreign object retrieval, sample collections, search and rescue, tool recovery, and then of course non-destructive testing application. And that is going to be really the focus for the rest of this presentation. Now, I've only got a very short amount of time to be able to share this information with you, and of course there's lots of we could spend a lot more time than the sort of 20 or so minutes that we have remaining to go through this. So again, if there are questions and we can't answer them immediately, or we can't provide as much information as you would like right now, then I would love to take this offline. We've got people that do my specific job in multiple locations around the globe, so it doesn't really matter where you're located. We'll have someone that will be able to assist you, or even possibly speak your language. Something that's I'm sort of cursed with here in the UK, that we tend to stick to English most of the time. And I think before we go on any further, I think it's interesting to, after we've looked at the applications, we can really study how we've got to a position to really understand as much as we do, and then start to innovate and develop products that actually really do work in these environments. And the industries that we are prevalent in, really, if we take the top 5, this generally includes oil and gas, power generation, nuclear, things like security and defense, and then utilities. And then we look at the applications, and we saw a brief snapshot of the type of applications, but we can simplify that even further and look at the 3 main applications as pipeline inspection, surface inspection, and vessel inspection. And then when you take a step back and look at all of these industries and all of these applications, we can see that all of these applications are generally shared across multiple industries. So what we learn from the oil and gas industry for an application or a solution that we provide, we can directly transfer that to other industries, and we can learn from all these industries, and they can generally benefit from each other. And that's something that's really, really beneficial from a robotics perspective, because essentially a pipe is always a pipe. So when it comes from a delivery perspective, the system that delivers the equipment or the sensor can generally be very, very similar. What might change would be the non-destructive testing technique. But let's look at some case studies, some examples of what we do. And I think I've chosen 2 today to try and, again, simplify it as much as possible. Now, there's hundreds of examples that we could talk about, and I've chosen 2 specific ones, one being a magnetic surface-based crawler, and one being a pipeline inspection crawler. So the first one we talk about is what we call a Mag 310. So some of you may have seen this in the past under its previous name of a Mag HD, which is a magnetic robot with a high definition camera. Now the Mag 310 is a slightly better name based on the fact that it is 310 millimeters wide, so we get some real understanding of what this means when it comes to this specific robot. So this robot is capable of traveling up to 100 meters. So it's a relatively long distance for non-destructive testing, relatively short distance from an Inuktun or Eddyfi Robotics perspective. It has a high definition camera with lots of different offset, multi-directional lighting options, and laser projection available for some scalar measurement. We've got a number of different types of actuators and arms, which can be used for the integration of sensors and probes. And of course, we can look at further integration for things like tooling and maintenance applications or surface preparation. One of the first probes that we've looked at using is one of these, a shark probe, which is a tangential eddy current array probe. So this is really designed for single pass crack detection, whether it's longitudinal or transverse cracks. It's got relatively wide coverage, and we can travel very fast with it. So we can travel at the top speed of the robot, which is around 7 meters per minute, I suppose, for an inspection scenario, and we can acquire data in that scenario. You've got a actuator mounted to the front of the robot, which can, of course, carry out a visual inspection at the same time as the crack detection inspection with the shark probe. We can lift the probe off of the surface when we're driving around to try and increase the life of the wear parts of the probe, and then we drop it when we want to get to a location where we believe we've found something that we would like to measure. Now, one of the benefits of this shark probe is that there's some compliance built into the bottom of it, and actually overall it's much less operator dependent compared to like alternative solutions, which is really beneficial when we consider a robotic solution that's being sent into a specific location. Something to consider. One of the other options that we have used frequently, and actually we've been doing some demonstrations today, so we'll have some videos available hopefully towards the end of next week, is with one of our dry coupled wheel probes. So we have an R-scan probe, which is available through our Silverwing Center of Excellence, and this has a magnetic encoders included, so it doesn't have to be used in a ferrous environment. It can be non-ferrous or ferrous, but the magnetic encoder wheels keeps the probe nicely in contact with the surface. Now, using this in conjunction with a robot is a great example of a encoded dynamic scanning UT system. We've got a probe. The probe itself is around 6 millimeters diameter. And actually, it's made out of the dry coupled probe. It means that we don't have to send couplant, for example. So say, for example, this MAG 310, and we're operating at up to 100 meters away, as an example. We might be in an environment where we don't want to use couplant or water to maintain that signal. Or we might be in an environment that actually is quite difficult to send couplant or water to the location. So actually the R-scan probe, if we're in a relatively well-prepared environment with no like major like corrosion pitting, for example, we can obtain good wall thickness scanning dynamically. Because without the requirement for couplant, because the dry coupled probe itself, the rubber material is the same velocity of water. So this effectively means we can negate the requirement for multiple for couplant itself. But like I say, this can be used by hand or attached to a robot. If you're in a scenario where you can carry out some external inspection in a relatively safe environment by hand, you can do that, and then you can mount this to a robot, for example, and carry out a robotic inspection in this particular scenario. One of the other examples that we look at is how do we operate in a marine environment. So we have multiple requests for operation of like thickness measurements, dynamic thickness measurements for things like FPSO hulls or ship hulls, or even things like jetty piles, like metal jetty piles, magnetic ones. And actually what we can do here is we can look at I'm going to turn the volume off because this video's got some terrible music. We can look at a specific solution for that. So here we have the same system. It's a magnetic robot. This particular application, there was a requirement to move some of the marine growth away. It was like some slimy marine growth. So we used a metallic brush on the front of the system. And then we have a UT probe attached to the front of this. Now, this particular UT probe has a 100-meter cable. You can see there's actually no interference of concern there. And we can get good B-scan data, so like a nice dynamic scan and an understanding of the thickness of the material. So this can be used 100 meters away, fully submerged in water. The complete system, the robotic system, is submersible to 100 meters. We've got cathodic protection on there, so it inhibits some of the corrosion that can occur from operating in salt water, for example. And of course, the probe design is such that the water becomes the couplant for that particular environment. So there's just another solution that we can look at. And finally, we've got examples where we look at pulsed eddy current. So pulsed eddy current is a fantastic solution where we're in an environment with potentially coatings So for example, there's a coating on a material. It might even mean that we can't magnetically adhere, so we're looking at this as purely a surface perspective. But pulsed eddy current, we've got probes that are able to be lifted away from the surface. The distance varies depending on the material that we're looking at and what we're trying to see, but it's a fantastic tool predominantly for screening, but also for some sizing of defects, which enables us to go through an area, get a good understanding of where there may be some corrosion, for example, underneath a coating or through a coating. And then any destructive testing that needs to take place can take place in a like pinpointed, rather than having to remove large amounts of coating or insulation, for example. It's a real strong benefit. So this does exist. I've only got an image, a rendering image here. So the majority of this is built up using like Delrin and stainless steel, purely because we don't want interference, like any magnetic interference through the pulsed eddy current. Now, if you want to talk in more detail about pulsed eddy current, or indeed any of the ultrasonic techniques that we talk about, or eddy current, then there's people that are much more qualified than I am. I think my background is very much robotics and visual inspection, but there's people that will be more than happy to take questions further on this. And then finally, we've got the visual inspection. So visual inspection is a really important part. Again, essentially it extends the reach of the human eye into areas that we wouldn't generally be able to see. And it's often overlooked as relatively subjective, but when you start to combine that with UT, other NDT techniques, for example, you really get a good understanding of what's happening. And we can be more advanced in the way that we capture our inspection data. So for example, we can take a vessel, and we can have a robot enter that, take lots of images, and just using software we can create a 3D model that we can manipulate and contains the image information inside. So this is a really good first step in understanding sort of the position of a robot and the position of indications, which becomes important when I talk later on about the real benefits for industry and the understanding of a scenario and how that works in these environments. And then finally, the last case study, I suppose, that I would like to consider is talking about one of our Tritrax 380 systems. So again, Tritrax has got 3 tracks. The 380 basically means it will fit inside a 380 millimeter diameter pipe. Actually, this specific custom solution will fit inside a slightly larger pipe because we have some things mounted to it. But we'll see this on the next page. But essentially, sometimes we need to travel in pipelines and we need to travel vertically, and the problem that you have traveling vertically is that if the pipe is made of a non-ferrous material, or if there's a large payload, then a magnet is not going to be good enough to be able to get us through that environment, especially when we want to start traveling long distances. So for example, the TT380 or the Tritrax 380, that can operate up to around 1,000 meters. It can operate vertically, not continuously vertical for 1,000 meters, but it can operate for 1,000 meters and with vertical portions. We can travel even further with fiber optics. We need fiber optics when we go past around 1,000 meters just for data transfer, for example. It can travel in both ferrous and non-ferrous pipes vertically, which is interesting. And the most important thing is that we can add a tooling arm and a shuttle to integrate multiple different sensors, probes, and tooling solutions to carry out pipeline inspection from the inside without the requirement to excavate or take various sections of pipeline apart, which is a real benefit when it comes to saving costs in excavation, civil engineering, etc. Quite frequently, we mount laser scanners to these. So you can see a rendering on the left-hand side. On the right-hand side, you see an example of a robot with a 2G Robotics ULS 100 laser scanner attached to the front, which will give us a good indication of internal pipe condition. There's an example here, so we can see a nice heat map with things like corrosion, any loss of material, ovality. You can carry out very good sub-millimeter accurate measurements using this type of technique, which is really good for internal inspection. Of course, if you can only access the inside of the pipe, you can use ultrasonics. Of course, you can use pulsed eddy current. You could use ACFM for various different parts of this pipe. Essentially, if you've got a very, very, very corroded pipeline, then you're not going to get good contact with conventional UT techniques. So actually, a laser scanner is a really good option for looking at internal corrosion and being able to map and both measure that. And it, of course, builds up a good 3D model, which is a nice visual representation for reporting purposes. What we can do is we can mount that to the front of the robot, and we can also mount a UT probe, so we can look at a UT array probe. You can see a close-up image of the shuttle attached to the front. So this is just a modified version or a customized version of one of the R-scan array hand probes, and we can control that with the robot. We can effectively create a 360-degree scan, which forms a donut. We can move forwards the width of the probe, do another donut. We can stitch all of these together, and we get a really good understanding of actually what the overall wall thickness is of this pipe. So unlike the laser scanner, which will only give us information of the inside of the pipe, this will give us the internal and the external information. So we get a really good understanding of remaining wall, which is really important for majority of applications. Again, I will mute the sound on this video and I'll talk you through it. But essentially, this specific robot, we can mount multiple sensors to. So we've stuck here to a laser scanner, a camera. Actually, there's a number of cameras on here. And of course, this UT probe. So the robot will drive forwards the width of the probe. In this case, it's around, I believe it's around 50 millimeters. It will do a 360-degree scan. We'll drive forwards another 50 millimeters, and then we'll start stitching these together. The laser scanner, again, of course, can be used for internal measurement. We can create a CAD file from the laser data, which you can then start to overlay the UT data to, which gives us a real nice 3D model with good, strong data and volumetric data attached to a 3D model. So you can see here you've got a good indication of where defects occur, the size of the defects, the location, most importantly, of that defect. So when you come to inspect the same thing in 2 years' time or 10 years' time, we can see if that defect size has increased, and we can see if there's any new defects, and we get a really good understanding of where that occurs within that particular vessel or pipeline, for example. What's our deliverable? I think if we take really three things, I think I've mentioned this in a previous discussion, is that we've got data. There's the analysis of that data, and then there's decision making. And effectively, if you look at a current inspection, we generally take images of a problem, or we obtain some inspection data using NDT sensors, and then we include that in a report. But it doesn't generally give us contextual information about exactly where the problem occurred, where it was captured, for example, where it was taken, unless the operator who was there specifically adds this manually, which gives an element of subjectiveness to it, and again, an element of lower repeatability, certainly for these internal inspections where we don't have a good understanding of where examples were captured. So that at that point, we really have just data. As much as we report on that and we can start to analyze it, that really is data. So before we start the reporting process, how can we try to improve this? One of the ways that we can do that is by using multiple sensor technology in one place. And that gives us a real 3D visual understanding of that. So if we take the example of the pipe scanning robot, which had a laser scanner and a UT scanner, phased array UT scanner, and some cameras, we can use all of that information combined with all of the encoded information to build up a 3D model, which is filled with the relevant contextualized data, which means that asset owners really can sort of start to step inside their assets. And actually, this gives them like a permanent record of inspection, so they can revisit that at any time. You can look at what happened last year, and you can compare these. You can see if something was potentially missed. You could find, if you find the new problem, you can compare that to the digital twin from previous years and see how an asset reacts over different time periods and with maybe even different product running through it. And you get a really good understanding of what's happening. And actually, we start to move much more from just data, just analysis, to tools that allow us to start to make these better decisions. And like I said at the beginning of the discussion, better information generally leads to better decision making. If you've got the tools and the information to make a decision, it's better than having less. So from an industry perspective, if we look at the takeaways from what we can offer from a NDT deliverable through robotics, and it's something that, like I say, there's so many other examples and options that we could talk about, and I really suggested there's examples that people have that are available now and examples where they would like us to try and explore this, and please do get in contact and we'll look at what the options are and how we can try and assist in these. But essentially, if you do have a problem that needs a solution, consider that these things, and that this is where really we try and focus our key areas of expertise, and that is we have much more modular systems, which allows for flexibility. So you can have a system that is modular, adaptable, for use on multiple applications. So you don't necessarily need to have lots of robots for lots of inspections. You can have a robot that is versatile, and you can adapt that maybe with different probes for different inspection techniques, or maybe for different inspection environments. We can travel very long distances with large payloads and a very, very small form factor. For example, we've got a crawler that will fit inside a 150mm diameter pipeline, and we'll be able to travel for around 1,000 meters. We've got systems that will fit inside smaller pipes and will travel 300 meters, as an example. So we can travel really long distances with a large payload with a very comparatively small robot, if you look at other options that may be available. We've got the capacity to integrate with other technology, and of course tooling for full inspection and maintenance. The real benefit with Eddyfi as a group is that we have all of this technology in-house, so we can very quickly look at what is the best solution, what will work. We're not competing against different technologies so much as that all these technologies come from the same place, and we just choose the best solution for that particular environment. Because of this, because you can put all of this technology together with multiple sensors to obtain this information, your probability of detection is of course increased. If you're using multiple data sampling and sensors to obtain information from the same environment, then you've got better information available to you. There's much less chance that you're going to miss a problem if it exists. You've got more chance of finding one if it's there. And this essentially means that you've got the best opportunity to really know your asset and make the best decisions associated with that. So that's really our key deliverable, is to provide you with the information that you need to make the decisions on the health of your assets. And that really is the end of my presentation. Of course, I'm going to switch over to the screens to look at the questions that we've had through. If I open up the comment section here, so I can see there's actually quite a lot of questions. So I'm going to go through the questions just in order of when they were asked, if that's okay. So the first one we have is, can we use phased array on a magnetic crawler? So the answer is yes. We would probably use a slightly larger crawler just because the payload might be a little bit heavier for a PAUT probe. So again, there's options. The PAUT probe that we showed in the last video of the pipe scanner, actually there's no reason why we couldn't mount that to a Mag HD, for example. We would have to look at the implications and where it's operating, whether it would be able to operate inverted, but we've got a considerably larger magnetic crawler with a considerably larger payload, the Mag 480, which would quite comfortably take a PAUT probe and inspect in those environments. Couplant delivery. I believed I mentioned couplant delivery before. So couplant or water as an example. Depends on the environment. Some environments you don't want to use couplant because you don't want to introduce water or moisture or even a liquid into these different areas, and in that case you've got really, if you're looking at welds, for example, you can look at PEC, you can look at ACFM for things like that, or you've got the option for a dry coupled wheel probe, like we mentioned a little bit earlier on. However, we have got solutions for delivering couplant. So the robot that we showed at the end, that had I didn't mention it, I should have done it, had a couplant dispenser. So it had basically a hose attached through the center of it. It's a water column probe, so it requires water constantly on that pipe scanner. What we do is we have water just pumped all the way through. Now, if we're going really long distances, or there's a more specific couplant, or we haven't got the ability to pump water externally, then we can have things like a bowser or a water container attached to the robot, which will give us access to that water. And then there's another question which I don't fully understand, but we'll get someone who's much more capable to answer this question. So, is it appropriate to look for corrosion in the HAZ near the weld by PAUT? So, I think I partially understand this question, but I don't want to get it wrong. So actually what we'll do is, if this question was asked on LinkedIn anyway, we'll get one of our PAUT specialists to best answer that question with the best information, because I don't think I'll do it justice. Damien, I see another question here as well. Is like, how do you send an NDT signal so far without noise? So it really varies. So for example, the UT probes, by definition, they're sensitive. When you start sending that information through a probe cable, for example, that signal can start to deteriorate for attenuation over different periods, over different lengths. Of course, if we look at the example of the ship hull inspection solution that we looked at here, the first video, that had a 100-meter cable and it worked. Doesn't necessarily mean that you can have a 100-meter cable for everything. When we start to look at that, we need to sometimes look at changing to a different tether. So we might look at like a Ethernet, or we might look at a fiber optic tether and then send the data that way. It might be that we look at mounting the acquisition device, so the boards from the acquisition device. I think of a Gecko or a Mantis, for example. We'll take the boards from that, mount them into a housing on the robot itself, and then just send data back as opposed to an NDT signal. So it really varies on the application. But there's lots of solutions available. So if you have an example where you're in a pipeline and you need to inspect 1,000 meters, then we can look. Most likely we would have a fiber optic solution with data acquisition on the robot itself being sent back. Hopefully that answers those questions. Exactly as this was come up on screen here. If there's any more questions, feel free to email me directly. If I don't know the answer, of course, there will definitely be someone within our group that will be better at answering those questions than I am. If I do know the answer, of course, I will provide the information as quickly as I can. But thank you very much for the time you've afforded me today. It's been really, really good to do this. And I look forward to hearing some more questions and potentially seeing you in field in the not too distant future. Thank you very much.